Testing. 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 Test. Okay. I think it's working. Dude, what? Ladies and gentlemen, please welcome your ML practitioners back onto the field. SoundStorm by Darude is a deep cut. That's some old techno right there. All right, so happy Monday. Hope you had a good weekend. Today we're going to be looking at SoundStorm. This is a viewer recommendation here. So SoundStorm Efficient Audio Generation coming out of Google Research. This is the paper website, which is a github.io website. And this is the actual paper. So they have some little samples here. So why don't we go ahead and just listen to this a little bit, see what they got.
About Google's paper on SoundStorm?
No, I must have missed it. What's it about?
Well, it's a parallel decoder for efficient audio generation, so it can even be used to generate dialogues.
Oh, interesting.
Yeah.
Oh,
yeah.
interesting.
This one's generated by SoundStorm.
Wait, what?
Wait, what? Okay, so we got some speech synthesis, probably a text-to-speech kind of situation. They got a bunch of different types here, but let's save these for the end once we actually kind of understand what's going on, because or else we're not going to know what the difference between voice prompt and synthesized dialogue is. All right. So abstract here. We present SoundStorm, a model for efficient, so it's probably going to be fast, non-auto-regressive. So auto-regressive means you're looking at your own output. So non-autoregressive means you're not looking at your own output. So like a recurrent neural network is a regressive, autoregressive. Anything that you look at the output of the previous step in order to make the next step, that's autoregressive. So non-autoregressive means it's not doing that. And the fact that it has the word efficient there means that it's probably doing either things in parallel or some kind of trick there, right? The fact that it's efficient and non-autoregressive, those two kind of go hand in hand. SoundStorm receives as input the semantic tokens of audio LM. So semantic means they have the meaning, which probably means the actual content of the audio in terms of the word. So the actual text content. I don't know what audio LM is. It's probably just the previous work by these authors or some kind of generic, let's see, audio LM. Audio LM is, it's the previous work from this same group. Zalan Borsos and Marco Tagliasaki. Zalan Borsos. So it's basically just the previous work by these guys. Relies on bidirectional attention. Okay, so more terminology here. So attention is the attention mechanism, which is basically a transformer architecture. There's other types of attention that aren't necessarily transformers, but that's pretty much almost always at this point when they talk about attention, they're talking about a transformer. Bidirectional means that it's working both ways. So if you have a sequence, whoa, what the fuck is that? If you have a bidirectional, LSTM is a good example. This is an older type of bidirectional thing, but a lot of models that look at sequences, they start from one side and then they go across the sequence. But something that's bidirectional can start from the beginning of the sequence and the end of the sequence at the same time and then kind of go both ways. And that's a technique that people used in order to make things faster. So there's a lot of different ways or different things that they could mean by bidirectionality, but we're already starting to get a lot of clues here, right? Bidirectional, non-autoregressive, efficient. Like I have a feeling all of this is going to be done in parallel. You're going to be doing little chunks of the whole sequence in parallel. Yep, and then here's the actual word parallel coming in. Confidence-based parallel decoding to generate the tokens of a neural audio codec. Okay, this is a very dense abstract, and I apologize for taking 10 hours to get through the abstract here. So what is a neural audio codec? So a codec is basically a method of encoding. It's a code that you use for encoding things, right? So there's video codecs, which are basically how are you storing and then transmitting a video in such a way that you don't have to transmit every single frame, right? And there's a variety of different video codecs. So there's the same kind of idea with audio. There's different audio codecs, which allow you to basically encode or compress the audio, send it to somewhere else, and then the somewhere else can uncompress it into actual audio. And there's a bunch of like hardcore, not hardcore, but like old school audio codecs. Right, let's see what old school audio codecs are. Comparison of audio coding formats. So you have MPEG or AAC, AC3, ALAC. Like you can see there's all these different kinds of audio codecs. FLAC, so this is kind of one that's known for super high quality. But more recently, people have started to use what are called neural audio codecs, which are basically codecs where rather than using, I don't know, some kind of Fourier series or some kind of fast Fourier transform or like some kind of fancy math or some kind of hard-coded algorithm, basically they have a neural network that's either picking the parameters of some algorithm or a neural network that's directly encoding and unencoding audio. So that's what they mean by neural audio codec. Okay, so basically you have this non-autoregressive, efficient, bidirectional attention mechanism that's decoding the entire audio in parallel, and then it converts it using some kind of proprietary special neural audio codec. Okay, we're starting to get a pretty good idea about what this is. Compared to the autoregressive generation approach of audio LM, so autoregressive generation is basically what most, for example, large language models are doing, where they generate one token at a time, and every token that is generated, you're generating it conditioned on the previous token, right? You're auto-regressing. You're looking at your own output as you go ahead and generate things one by one. But the problem with that is that it's slow because you have to wait for each step before you can take the next step. Our model produces audio of the same quality with higher consistency in voice and acoustic conditions while being 2 orders of magnitude faster. Damn, okay. That's a lot faster, but I mean, we don't know whether audio LM was just super slow to begin with, so SoundStorm generates 30 seconds of audio in 0.5 seconds on a TPU v4. Sounds impressive, but I don't necessarily know off the top of my head whether that's impressive or not. It kind of sounds impressive. 30 seconds of audio in 0.5 seconds on a single TPU. I don't know. We'll see if they have other benchmarks and whether or not that's super impressive or not. We demonstrate the ability of our model to scale audio generation to longer sequences by synthesizing high-quality natural dialogue segments, given a transcript annotated with speaker turns and a short prompt with the speaker's voices. Okay, this is interesting because it basically means that you can generate audio with different speakers, right? So like, I don't know. I guess I'll stop there. We'll see exactly. Google research GitHub IO SoundStorm.examples. Okay, this is just the GitHub page. Okay, so I don't know if they actually have the exact code. Let's see if we can find the code on GitHub. They probably didn't post it on GitHub. Google Research CNET. This repository multimodal. So this is the same people, Zalan Borsos here, but let's actually go into this guy's, I can't even like click on his name. What the fuck is this? What? Is this guy like a ghost? Can I not find this GitHub, this user? Here we go. Zalam Borso. So I'm looking to see if he's committed code anywhere, but he is not. Okay. So whenever I was working at Google, none of my commits actually were with my public GitHub account. So even though this guy, it looks like he's not doing any committing here, if you look at the history, there's no commits. He's probably writing a lot of code. It's just that it's all within Google, because in Google you work inside this mono repo. So you push into this mono repo, so your public GitHub gets absolutely no activity. But it doesn't look like he's created this SoundStorm repo. So far there are no public code. There's no public code for this from what we can see. All right, introduction. Modeling discrete representations of audio produced by neural codecs. Discrete representations of audio produced by neural codecs. So I think that's the neural audio codecs. Makes the task of audio generation amenable to the powerful transformer-based sequence-to-sequence modeling approaches. So, what do they mean here? Is that in order for audio to be turned into a sequence so that you can use something like a transformer, you're going to need to basically discretize it. So, discretize it into tokens is, I think, what they're referring to here. Casting unconditional and conditional audio generation as sequence-to-sequence modeling has unlocked rapid progress in speech continuation. Unconditional and conditional audio generation, so you can either generate audio conditioned on something or not conditioned on something. They're probably going to condition it on the speaker and the text. For generating high-quality audio by modeling the tokens of a neural codec. I still don't really know exactly what the tokens of a neural audio codec are, but hopefully they explain that. The rate of the discrete representation must be increased, resulting in either an exponential growth in the codebook size or in long token sequences. So the codebook size is basically how many different possible tokens exist, right? So whenever you tokenize text, for example, for use with an LLM, we saw in an earlier stream how I think it's called like sentence piece is a common tokenizer that's used, and the total amount of individual tokens or unique tokens in that is something like 30,000 tokens, right? So the size of that is 30,000. The codebook size for that LLM tokenizer is 30,000. I don't know what the codebook size is for an audio codec, but what they're saying here is that as you increase the rate, I assume maybe they mean the sampling rate or maybe the resolution at which you sample the audio, the size of the actual audio codebook can increase to the point where you can't really use it, right? And long token sequences here refers to the sampling rate for audio is just how finely are you cutting up time, right? So if you have 1 second of audio, if you have a sampling rate of audio, I think 1600 hertz is a common one. But actually, this is a nice little thing here, right? Low sample rate means you're cutting up time into these bigger buckets. Higher sampling rate means you're cutting up time into these smaller buckets, right? So here's a standard kind of audio sample rate, 48 kilohertz, which is actually a lot, right? That means hertz is per second, so kilohertz is 1,000 times per second. 48 kilohertz is 48,000 buckets per second, right? Which is a huge amount of little samples within a specific second of audio, right? So if you're sampling at 48,000 kilohertz, that's a lot of tokens. That's 48,000 tokens per second of audio, which means that any kind of sequence to sequence based kind of architecture is going to have to chew through a huge long sequence of tokens. While the exponential growth of the codebook is prohibitive due to memory limitations, in turn, long token sequences also present computational challenges for autoregressive models. In particular, attention-based models, which are the main focus of this work, will incur quadratic runtime complexity. Okay, so if you're not new to the channel, you've probably heard this rant before, but attention-based models such as transformers have this fundamental flaw that they're quadratic in terms of the amount of memory and compute that they use, basically because the way that they work, every single part of the sequence has to pay attention to every other part of the sequence, kind of like this, right? You have a square and you have a sentence, you have the same sentence, and you're going to have to calculate the attention score for every word and every other word. So as your sequence increases in length, the total size of the compute or the total compute footprint is going to increase quadratically, right? Quadratic square, which is n times n. So if they're already concerned about the fact that the sampling rate of audio leads to long token sequences, then using a transformer is going to be even more sketchy because imagine 1 second of audio sampled at 48 kilohertz. Now you have a 48,000 long sequence multiplied by a 48,000 long sequence. The total memory footprint of that is absolutely massive, all right? Addressing the trade-off between perceptual quality and runtime is one of the core challenges for audio generation. So being able to trade off between those two things. The problem of generating long audio token sequences can be addressed by at least 3 orthogonal approaches or a combination thereof. Efficient attention mechanisms. Okay, so lots of different ways that people have come up with in order to not have to do this quadratic attention situation. Sparse attention, masked attention. There's a lot of them. Non-autoregressive parallel decoding scheme. So this is kind of similar to what we saw with the megabyte paper, which came out of Facebook, where, hey, rather than doing the entire sequence basically end to end, like all the way from the beginning to the end of the sequence in one giant transformer, break it up into little chunks and then do each of the chunks separately, right? So this kind of like parallel approach. The problem with that is that it's non-autoregressive, right? So you're going to be breaking it up into chunks, but some of those chunks are not going to have any knowledge of the other chunks, right? So you kind of trade off the fact that each individual little chunk that you're going to be decoding is not going to have any information from the other chunk. So you're losing a little bit of potential signal there, but you can do it in parallel, which means you can do it a lot faster. And then finally, the third approach here is called custom architectures adapted to the special structure of the tokens produced by neural audio codecs. Okay, so I don't know much about this, but it sounds like it's basically people have come up with special architectures that are over-engineered probably to the specific nuances of neural audio codecs. Anytime I hear that, custom architectures with special structures, I feel like I just think about over-engineering, and somebody in a couple years is going to come up with something more simple and more generic, and they're going to beat that out. So generally, super custom, super special stuff just loses out over time. However, in the context of modeling the token sequence of neural audio codecs, either unconditionally or based on weak conditioning, okay, so unconditionally means they're not whatever neural net is producing the output, right? These token sequences for the neural audio codecs, whatever thing is producing that, it's either not conditioned on anything or weakly conditioned, where they define weakly conditioned as just giving it the text. The efficient generation of high-quality audio segments still remains an open problem. We believe that it is the special structure of the audio token sequence that holds the most promise for future advances in long sequence audio modeling. Okay, so special structure of the audio token sequence. I don't know what this special structure is, but I think they're going to let us know. Concretely, both SoundStorm and encodec rely on residual vector quantization. Okay. Residual vector quantization is where each compressed audio frame is quantized by a series of quantizers. So quantization is just the process of taking something and making it smaller, right? So quantization in the context of, for example, the weights of a neural network, something that people do all the time. is they will take the weights of a neural network, which might be in floating point 32, so something like this. This is a very good little picture here, right? And you're spending a bunch of memory, right? 32 bits of memory to store all of this, right? To store this number 0.68. So you can quantize it and store it as an integer 8, which is whatever 1/4 of this, right? Way less memory. So that's quantization in the space of neural network model weights. But quantization is also just a more generic term, and it refers to basically breaking things up into smaller chunks, right? And you lose signal. So quantization is lossy, right? And what I mean by that is that you're losing some of the original resolution of whatever you're quantizing whenever you quantize. So I think when they refer to quantization for this residual vector quantization, the mental image you should have is something like this, right? Where you have your pure audio signal, right? Which kind of is infinite resolution. And then you have your quantized audio signal, which is going to be cheaper to represent, and you need less numbers to represent it, but you're also losing information, right? It's kind of lossy inherently. Each quantizer operating on the residual of the previous one. So the number of quantizers controlling the overall bit rate. So residual generally means the difference. So basically, let's say that you had this, right? You had this blue is your quantized signal, and then this red is your real signal. The difference between the red and the blue is going to be your residual. And then you can basically take that residual and quantize that. So residual vector quantization. See if we can find a nice little pic for this. We can't find a nice little pic. This is another YouTuber here. Okay, there are no good picks for residual vector quantization, but I think it's basically an iterative kind of thing where first you quantize the whole audio signal, then you basically subtract the quantized audio signal from the true audio signal, get the residual, and then quantize the residual, and then do the same thing again, right? And then however many of these quantization or quantizers you want to have is going to basically control how much memory you do, but you're going to or how much memory and compute you're going to use, but you're going to trade it off with quality, right? So if you don't have a lot of quantizers, it's going to be very cheap, very fast, but the quality isn't going to be there. And the opposite is also true. If you can have a ton of quantizers, your quality is going to be high, but the overall bit rate is going to be low, or it's going to be high. Sorry. This induces a hierarchical token structure. So hierarchical means multiple levels, where tokens from the finer RVQ levels contribute less to the perceptual quality, allowing for efficient factorization. So I think what they're referring to here is that the first quantizer, right, the lowest level quantizer, the one that you're using at the very beginning, the one that's doing this this blue stuff, right? So let's say this blue one is the first quantizer. This one is going to have most of the information, right? Then once you take the residual and quantize the residual, that first quantized residual is going to actually matter less. It's going to be less important for the perceptual quality. And then once you quantize the residual of the second quantizer, it's going to be even less, right? So there's this kind of like hierarchy where the very first quantization step is going to be the most important in terms of perceptual quality, right? So it sounds like they're going to have a different tokenizer for each level on this RVQ, our residual vector quantization, allowing for efficient factorizations and approximations of the joint distribution of token sequence. Hence, the models and decoding schemes should take this special structure of the input into account for efficient trading and inference. Okay. The models and decoding schemes should take this special structure of the input into account. So the fact that because we know we're using residual vector quantization, we know that the perceptual quality, the importance, if you want to think of it that way, of the very first couple quantizations are more important in terms of the actual final perceptual quality of the audio than the later quantizations. We know that we should spend as much of our model capacity, as much of our kind of training budget, whatever you want to do, you should spend more of your effort on those very first levels of this RVQ hierarchy. Okay, in this work, we present SoundStorm, a method for efficient and high-quality audio generation. SoundStorm addresses the problem of generating long audio token sequences by relying on an architecture adapted to the hierarchical structure of the audio tokens. So some kind of special architecture that they're going to introduce that abuses the fact that you have this hierarchy and this RVQ quantization. A parallel non-autoregressive confidence-based decoding scheme inspired by mask GIT. So the second part is going to be the fact that they have this non-autoregressive kind of parallel approach, right? Which means that they can do it all at the same time, the entire sequence largely at the same time, which is going to come down to breaking it into these little chunks and then doing each of the chunks independently. I don't really know exactly what confidence-based decoding means. They might have they might decode the same chunk multiple times and then pick the one with the highest confidence. That would be my guess, but I'm sure they'll explain it later. And SoundStorm relies on bidirectional attention-based conformer. Okay, so this is probably this specific inspiration for their bidirectional attention mechanism that is trained to predict masked audio tokens produced by SoundStream given a conditioning signal such as the semantic tokens of an audio LM. Okay, so whenever you're doing an autoregressive attention mechanism, generally the way that you train that, for example, GPT is a generative pre-trained transformer. The way that that's been trained is by next token prediction, right? So you basically give it everything in the sentence up until this word, and then you have it predict that word, right? That's how a generative pre-trained transformer is trained. Next token prediction. But if you're doing a bidirectional non-autoregressive attention mechanism, you don't have to limit yourself to just the beginning part of the sentence. You can actually do the whole sentence, right? Because you're looking at the whole sentence at the same time. So what you end up doing is you take the entire sentence, mask out a specific word in that sentence, and then try to predict that specific word given the entire sentence, right? And every time I say sentence and word, just replace that with audio snippet and a specific little chunk of the audio snippet. Giving a conditioning signal such as the semantic tokens of audio LM. On the input side, it sums up the embeddings of the tokens corresponding to the same SoundStream frame. Sums up the embeddings of the token such that the internal sequence length for the self-attention is identical to the number of SoundStream frames. Okay, this sounds confusing, but I think it's probably just because we're gonna eventually look at this figure, and I feel like it'll kind of make more sense there. Describing a model architecture only in text is always more confusing than just looking at the actual image IMO. Is identical to the number independent of the number of quantizers. So again, the number of quantizers in this residual vector quantization process is going to determine the trade-off of audio quality and speed. The output embeddings are then processed by separate heads. So transformers, obviously you can have a bunch of heads in parallel, right? Per RVQ level to predict the masked target tokens. So you have separate transformers heads per RVQ level, and then they're predicting the masked target token. So they're doing a masked prediction task, right? So they have the entire audio sequence. They mask out one specific little chunk from it. They residual vector quantize the entire audio sequence. You have a separate transformer head for each quantization level. right? Where the first one's actually going to be more important than the second one, which is going to be more important than the third one, and so on. And they predict the part of the audio sequence that is masked. And they're not predicting in like actual audio space, they're predicting in token space. At inference time, given the conditioning signal, SoundStorm starts with all audio tokens masked out and fills in the masked tokens RVQ level by level over several iterations. This is a little sketch, right? Because they say non-auto-regressive, but here they're conditioning on previous RVQ level, so it's auto-regressive in the sense of it's going RVQ like level by level in the RVQ kind of dimension, but it's not auto-regressive in the sense that it's looking at the whole sequence. So that's a little confusing there. Predicting multiple tokens in parallel during a single iteration within a level. To support this inference scheme, we propose a masking scheme for training that mimics the inference procedure. Okay. So whatever they do in training is going to mimic what they actually end up doing in an inference. So inference is when you actually use the neural network to do something. We demonstrate that SoundStorm can serve as AudioLM's acoustic generator, replacing both AudioLM's Stage 2 coarse acoustic model and Stage 3 fine acoustic model. Okay, so I haven't really read AudioLM paper, but it basically sounded like they had a couple stages, one kind of coarser stage and then one finer stage. SoundStorm produces audio 2 orders of magnitude faster than AudioLM's hierarchical autoregressive acoustic generator. So AudioLM's autoregressive generator. So if AudioLM was autoregressive, it has to generate it one kind of audio token at a time. So, of course, the fact that this one is non-autoregressive and it can do the entire audio sequence at the same time in parallel means that, of course, it's going to be significantly faster. But whether or not SoundStorm is 2 orders of magnitude faster than some other random state-of-the-art audio generator is not entirely known, right? They're only comparing against this specific AudioLM, which was probably very slow. Matching quality, improved consistency in terms of speaker identity. We show that SoundStorm, coupled with text-to-semantic modeling stage of SPEAR TTS, so TTS is text-to-speech, and I don't know what this one is, but it's probably some kind of fancy text-to-speech, can synthesize high-quality natural dialogues, allowing one to control the spoken content and speaker voices. So this is probably going to be the conditioning. So what are we going to condition our audio generation on? We're probably going to condition it on the actual content, so basically text. We're going to condition it on the speaker voices, so either some kind of embedding that represents a specific speaker, or maybe, I don't know, maybe like they say here short voice prompts, so maybe like a 10-second clip of someone talking, and then that gets turned into an embedding, and then you condition the generation on that embedding. And speaker turns via transcript annotations. Okay, so in their example here, right, the example that we heard, they basically have 2 different people talking to each other, so being able to switch from one person talking to the other person talking. When synthesizing dialogues of 30 seconds, we measure a runtime of 2 seconds on a TPU v4. What? This is... what? This is different than what they said up here. 30 seconds of audio in 0.5 seconds on a TPU v4. And then you scroll down and they say 30 seconds of audio in 2 seconds on a single TPU v4. So that's a little weird. One of those is wrong, or they're talking about different things, but that's a little sketchy. The fact that they have 2 different run times. Okay, related work. So lots of related work here. Modeling the token of neural audio codecs. So again, neural audio codecs is basically just a codec. I think it depends on how they condition the model. Okay, so basically an unconditioned version of this is going to be faster, and then of course if you condition it, you're going to have to create an embedding for the speakers or something like that, and then that's where the extra 1.5 seconds of runtime is coming. I think you're right, Oizen. Unsupervised speech embeddings have provided a low frame rate representation of the underlying signal, which remains rich enough after discretization for language models to generate intelligible speech from a specific speaker as a sequence of tokens. Okay, so unsupervised speech embeddings. What do they mean by this? So a token and an embedding are two words for the same thing. At the end of the day, a token and an embedding are both referring to a vector in a high-dimensional space, where that high-dimensional space has been shaped over time through a training process, right? So the same way that the tokenizer that you use for an LLM has been trained with some kind of unsupervised task for a very long time on a very large corpus of generic data, there's probably an equivalent thing in the audio space where you have some audio tokenizer, right, which takes your audio signal, your raw audio signal, and turns it into these tokens which basically are representing the underlying signal, right? And what they're referring to here with the rich enough after discretization means that your tokenization process is going to lose some information, right? Anytime you take a high-dimensional input signal such as audio or maybe an image and you embed it or tokenize it, you're compressing that information, right? So you're going to lose some information in that process. But they're saying that, hey, people have been doing this for a while now. Here's a 2020 paper, 2021 paper, and these unsupervised speech embeddings, right, these tokens that people use for audio are pretty good, and people have been able to use them to generate speech for specific speakers and so on. So they're kind of arguing that, you know what, they're pretty good already. We're just going to use one of these tokenizers probably. Neural audio codecs, with the ability of reconstructing high-quality audio at very low bit rates, subsequently allowed for extending discrete modeling to audio signal as diverse as multi-speaker speech and piano. Okay, so people have been using this for multi-speaker speech and piano, music, sound effects. All these papers are relatively recent. Like one thing I'm noticing here, 2020, 2021, 2021, 2023. So it's not like you're getting a reference to a neural audio codec paper from like 2005, right? So it seems like neural audio codecs are relatively new. I don't know. All these references are new, so still seems like it's early in the field. In particular, Audio LM introduces a hierarchical... I love this. He references his own paper. Anytime I see that, I think of this like meme where it's like Obama medal on himself. Yeah, like this meme. It's like citing your own paper in your own paper, you know? You cite your paper in your paper so you can get more citations. Introduces a hierarchical sequence-to-sequence approach where high-level semantic tokens are generated as an intermediate representation, which are then used to condition a signal for predicting tokens of a sound stream. High-level semantic tokens. So, kind of from what I've been reading, it seems like there's different tokenizers here. You have the tokenizer that actually converts it into this neural audio codec tokens, and I think they're referring to these as audio tokens. And then whenever they talk about semantic tokens, I think that might be taking a sentence, like an actual, like an English sentence in text, and then converting it into basically the tokens that you would use in an LLM, right? So I'm not 100% sure because I don't exactly know how they're doing this, but I think there's two different tokenizers here. There's semantic tokens, which are basically the actual text, and then audio tokens, which are a compressed version of the audio signal itself. Yeah, so the text tokens, which they're calling the semantic tokens, are used to condition a model which predicts the tokens of the codec. So it's a sequence-to-sequence task, but you're using different tokens in the two different sequences. While this hierarchical approach has demonstrated remarkable results for speech and music modeling, the computational cost of modeling flattened SoundStream tokens with self-attention scales quadratically with the sequence length and thus the bitrate of the neural audio codec. Yeah, so anytime you have a self-attention mechanism on some kind of sequence of tokens, you really want to make that sequence of tokens as short as possible. And because the way that audio works, you want to sample it as finely as possible. There's going to fundamentally be this trade-off of like how fine is your resolution at which you're sampling, and then how much memory are you and compute are you spending because you have now this huge sequence of tokens. Preventing these models from generating long-form audio with high quality. SoundStorm alleviates this issue by modeling the multi-level tokens of the neural audio codec in parallel, introducing a 2 order of magnitude speedup over autoregressive modeling, and unlocking the ability to scale audio generation in both quality and sequence length. So this is actually very similar to the paper that we read last week, the megabyte paper, right? So in the megabyte paper, they were saying, hey, there's this problem with large language models where because they're autoregressive, they have to basically generate a sequence token, one token at a time, and it makes it very slow, and it also reduces the total size of the input sequence, right? This context. So the solution that they had was largely saying, hey, let's get rid of this autoregressive kind of constraint in our design space, and that allows us to do things in parallel, which means that one, now not only can we do things faster, but two, we can also be doing things with a much longer sequence. So this is kind of that same idea, but in the audio space. Excited for this one, Mask GIT. I don't know what Mask GIT is. Let's see, Mask GIT. Masked Generative Image Transformer. So it's basically just a image transformer where they mask out specific parts. I might have even read this paper. Let me see. As soon as I see the figures, I will know if I read this. Yeah, I read this. Okay. So autoregressive, right? Autoregressive transformer requires the previous parts of the sequence in order to generate. So here, right, if you're doing an autoregressive transformer, if you want to predict this little pixel right here, you need all the pixels beforehand, right? So you can only predict one pixel at a time. If you get rid of that autoregressive constraint, you do it in parallel, you can basically, you get the whole sequence at the same time, and you can predict any token in that sequence conditioned on the entire previous sequence. So you can see here how you can basically do it in parallel a lot faster. And the way that these are generally trained is that you basically start from real images and then you'll mask out certain parts of the real image and then you'll basically generate the parts that are missing. And you do that on a huge data set for a long amount of time, and then you end up with a non-autoregressive transformer that is quite good. This is pretty cool. Okay, back to SoundStorm though. Led into some efficiency improvements that SoundStorm is claiming. Yeah, I mean this paper, the Mask GIT, and I think the Megabyte, like they're all basically the same idea, and it's just get rid of this autoregressive and then just do it in parallel is basically the TLDR. Yeah. A common design choice for modeling RVQ token sequences is to sum the embeddings corresponding to the same RVQ input embedding. So RVQ, residual vector quantization tokens. So there's probably a token for each level of the RVQ, right? Corresponding to the same RVQ embedding frame, summing the embedding. So each level of the RVQ, right, where the RVQ is like a series of quantization steps where you quantize the signal, and then you get the residual of the quantized signal and the real signal, and then you quantize that residual, and then you do the same thing again. You quantize that residual, and you quantize that residual. So it's almost like yeah, whatever. I won't go there. But basically, it seems like for each of those quantizers, you're going to be able to get an embedding, and then they're just going to sum up these embeddings in order to get like one generic embedding. The problem I see with that is that if you sum the embeddings, you're going to lose track of the fact that this embedding corresponds to the first one and this embedding corresponds to the second one, which is really what they were talking about here, right? Is that you want to take into account the fact that the RVQ has a kind of hierarchical level where the first levels are more important. So it seems kind of sketchy to sum the embeddings because you're just going to lose the fact that you know that that first embedding is going to be more important. But maybe I'm just not understanding exactly what they're saying. Operating on such sequences, AudioGen proposes a transformer with Q separate heads for each of the different RVQ levels. Right, so you're going to basically have a different transformer head for each of these RVQ levels. I don't know how many RVQ levels there are. Like, what's like a standard number for RVQ? Let's ask Bard. What is a common number of quantizers in a RVQ? Like, are we talking 10 or are we talking like 1,000? Typically between 2 and 100. Okay, so it's like on the order of magnitude of 10. 12 in the paper. Okay. Predicting the tokens from an RVQ frame in parallel while providing a significant speedup for inference, the authors found that for text-to-audio generation, this approach has an inferior performance compared to modeling the token sequence of an neural audio codec with similar bitrate and reconstruction quality with single level of quantization. Interesting. So basically there seems to be this difference where like, hey, are you generating the audio directly or are you generating the tokens for a neural audio codec? And then you're using that neural audio codec to actually get the raw signal or the raw audio. And they say here that even with a single level of quantization, going in using this kind of intermediate representation of the neural audio codec is going to not only be better but also faster. All right, you have val E. You can see they tried very hard to get wall E, but they couldn't, so it's val E. Instead relies on a hybrid approach where tokens corresponding to the first RVQ level are predicted autoregressively and the subsequent levels are produced non-autoregressively. Ooh, okay, so here's kind of a weird hybrid kind of situation going on here where you use a autoregressive kind of strategy for the first RVQ level, right? Where the first RVQ level is going to have the biggest kind of signal to noise, or I guess it's going to encode most of the information, right? That first level of the RVQ hierarchy is going to be where all your juice is really at, and then every level after that is kind of less and less important. So use an autoregressive model for the first level, and then the levels after that just use this non-autoregressive strategy. The latter is achieved by a model that sums up the embeddings from the same RVQ input frame and applies bidirectional self-attention to predict all tokens from the RVQ level Q plus 1, given all tokens from the level 1 to Q. So this is autoregressive, right? If you're predicting Q plus 1 from 1 to Q, then you're autoregressive in the sense, or within the space of RVQ levels. That's kind of what's a little bit confusing here, is that there's two levels of autoregressive that you could be considering here, right? Whenever they say autoregressive versus non-autoregressive, they're referring to the sequence, right? Where they're like, it's not autoregressive in the sense that in order to predict element n of the sequence, you're not limited to just 1 to n minus 1 in terms of the sequence, but they're autoregressive in the sense of the RVQ levels, right? So if you're generating RVQ level Q plus 1 based on RVQ level 1 to Q, isn't that autoregressive in regards to the RVQ levels? So there's multiple dimensions here, and I feel like it's a little bit confusing because of that. During inference, tokens starting from the second level of the RVQ are produced iteratively, performing greedy decoding, choosing the most likely tokens level by level. Level-wise, greedy decoding represents the baseline for our method. Right? Produced iteratively, level by level, aka autoregressively. Modeling sequences produced by RVQ has also been investigated in all domains other than audio. For example, the RQ transformer also adds up the embeddings corresponding to the same RVQ input frame, but factorizes the full joint distribution efficiently with a spatial and depth transformer. Okay, so some kind of fancy technique here. While it has been demonstrated, this approach, potentially coupled with parallel decoding schemes, is a promising future avenue. Factorizes the full joint distribution efficiently with a spatial and depth transformer. Okay, I don't know. I don't think we're going to understand what this Lee et al. 2022 paper is based on like one sentence, but apparently the authors of this paper think that combining whatever this approach is with the approach in this paper is a promising future avenue. Parallel decoding. In order to improve the inference time and allow bidirectional non-causal attention on the input sequence, parallel decoding schemes have been proposed for text. Okay. Images and video generation. Yeah, so parallel decoding is popular anywhere you have sequences and transformers, which at this point is pretty much every single type of modality. Of particular relevance to our work is the parallel iterative sampling scheme of mask GIT. Mask GIT starts from masked tokens and in each round predicts a portion of the tokens based on confidence scores. Okay, so that's where the confidence scores is going to come in. Is basically you're going to predict a portion of the, so you get the entire sequence. Your model can look at the entire sequence, right? You're doing this in parallel. It predicts some parts of that sequence based on the confidence. So wherever the highest confidence is, it'll predict those. There's going to be some kind of threshold, probably some confidence threshold. And then once you actually have part of that sequence filled in, then the confidence on other parts of that sequence are going to start getting filled in, and then so on and so on and so on. So it kind of makes sense here that like once you get this one, right, the eyeball of this flamingo, then you kind of know what the areas around the eyeball are going to look like. And then once you kind of know where the area around the eyeball is going to look like, then you kind of know where the beak is going to be. So it's like, right, as you have more and more of the sequence available, the confidence for each individual token is going to get higher and higher and higher because you kind of know more and more about what the full sequence is going to look like. So that's kind of where this iterative confidence-based decoding is coming in. I actually really like this picture. So they're basically doing this, but in the audio space, right? So rather than thinking about this giant square of pixels, just think of it as every single one of these little squares is like this long string of little squares that represents the audio. Pretty cool. Feels quite a lot like diffusion. In a sense, yeah, like at a high level, right? But diffusion, what you're doing is you're removing noise. Here, you're basically predicting individual tokens. The portion of the predicted tokens in each round is controlled by a schedule and usually progressively increases over the iterations. Yeah, so this is maybe the problem, is that not only is there going to have to be some kind of confidence threshold, which you're going to have to define. So there's going to be some hyperparameter that is the confidence threshold. Then there's going to be some hyperparameter that is the portion of predicted tokens each round, right? So you're going to have some schedule. So this is kind of a problem, right? You have hyperparameters for the confidence. You're going to have some kind of fancy schedule. So the more hyperparameters like that you introduce, the more annoying it is to tune, the more difficult it is to know that you're doing something optimally. So I generally don't like to see that. Yeah, they explicitly use the model confidence. It's really cool. Okay. Once predicted, the tokens are treated as fixed. Our proposed decoding scheme can be seen as an extension of mask GIT's decoding to token sequences produced by residual quantization. You could probably do residual quantization on image space as well, right? Because you're predicting a token, and then you can take the difference between the predicted pixel or little token and the true pixel or token, and then that's the residual, and then you could basically quantize that. So I think the cool part about audio and image is that both of them are kind of natural modalities, right? It's like both images and audio are kind of, they're coming from the real world, which is this kind of like infinite resolution input. And I feel like any technique that you use for audio, you can use for images, and any technique that you use for images, you can use for audio. You're not going to use the same exact thing because audio is kind of one-dimensional with time, and images are two-dimensional, and then you can have two-dimensional with time, which is video. But a lot of the same kind of techniques and kind of high-level thoughts and intuitions that you are applying to audio can also be applied to images and back and forth. So if you're looking for things to do research on, you can do exactly what these people did, right? Where they said, hey, here's a cool computer vision paper, let's apply it to audio. You could do the same thing where you could find some cool audio paper and then say, how can I apply this to the image space? So there's a lot of potential ideas to be had by looking at audio things for images and looking at image things for audio. SoundStorm receives as input a sequence of discrete tokens representing the conditioning signal and produces an output sequence of SoundStream tokens. Okay, so you're going to have, it's a sequence-to-sequence task, but the input tokens are going to be what they're calling semantic tokens, which is probably going to be the actual text. And the output is going to be these SoundStream tokens, which are these audio codec tokens, which are then decoded back into an audio waveform with whatever the SoundStream decoder is, right? That's probably pre-trained and frozen, right? So whatever neural audio codec they're using is going to be probably pre-trained and frozen. We assume that the conditioning signal is time-aligned with the SoundStream frames or can be upsampled to the same rate. Okay, so here they're basically saying that because the generation is conditioned on the semantic tokens, you have to make sure that those semantic tokens are time-aligned, right? They correspond exactly with the audio at that specific time, or can be upsampled to the sample rate. Such a conditioning signal is, for example, the semantic token sequence used in audio LM, Spear TTS, or music LM, which makes our method a drop-in replacement for the acoustic generators of these models. Okay, so they're using the same semantic tokenizer in these other papers, audio LM, Spear TTS, music LM. I bet you it's probably just like a generic text tokenizer. We leave the extension to other types of conditioning signals via cross-attention or to unconditional sampling from future work. Unconditional sampling is crazy, right? Like, what type of audio gets generated when you unconditionally sample, right? Like, I wonder what actually comes out. For future work and focus our presentation of SoundStorm with the acoustic generator replacing both audio LM's coarse and fine acoustic modeling stages. The architecture of the model is illustrated in Figure 1. At the input side, we interleave the time-aligned conditioning tokens with the SoundStream tokens at the frame level. So frame here, the size of the frame is going to be determined by the sampling rate of your audio. Right, so one frame is going to correspond to one little chunk of audio. And very similar how, like, whenever you have video, you have this frame rate. You basically have the same thing with audio, except usually it's called the sampling rate. Audio LM's semantic tokens are generated by k-means on intermediate representations of a W2V BERT model. Okay, so a W2V BERT model, I don't even know what that is. W2V BERT. W2V BERT is a wave to vec BERT. Cool. Speech sequence to sequence. Okay, so it's not just a tokenizer used for LLMs. It's like a tokenizer that's already kind of specific to audio. So it seems like the semantic tokens, I guess it makes sense, right? Because whenever you tokenize something for the purposes of like a large language model, like a GPT or a chat GPT or something like that, you want those tokens to represent the meaning of the word, right? But probably when you're doing this type of audio situation, you want the tokens to also represent the meaning, but you also want them to represent things like the phonemes, right? Or like you want them to represent like the specific kind of sounds that it's producing. So I could see why you would use a kind of a different tokenization situation for this audio generation than you would use for a large language model. Sum the embeddings corresponding to the same frame, including the embedding of the conditioning token, and pass the resulting continuous embeddings to a conformer. Okay, so they're combining the embeddings. Tokens considered in the loss, masked tokens, conditioning tokens. SoundStorm tokens. Q and T. Consequently, the sequence length for bidirectional self-attention in the conformer is determined by the number of SoundStorm frames, typically 50 per second. That seems low. Usually audio sample rates are way higher than 50 per second, so this is a little weird. And thus is independent of the number of RVQ levels Q, allowing one to handle audio with length on the order of minutes. At the output side, we use Q-dense layers as heads to produce target SoundStorm token. So the number of heads is going to depend on the levels of this residual vector quantization, RVQ. Okay, so finally we get to the actual architecture diagram. So let's go ahead and read this. We got SoundStorm architecture and masking scheme for training. So this is training. This is not inference. The model reduces the input sequence length by summing up the embeddings of the tokens corresponding to the same SoundStorm frame. So summing up the embeddings, that's what this little plus here is. So this little, can I draw something? There we go, boom. That's what that little plus is the sum. I think this little thing here, this little little thing here is the actual thing that's doing the tokenization, right? So this is the converting whatever this input is here, this little red dot, into some kind of embedding, and then that embedding is being, or maybe it actually represents the embedding itself. So you see here how the embedding is a little vector, and then you're summing it up with all these other little vectors, and then you get one kind of joint embedding, if you want to think of it that way. And that's what's actually being consumed by this conformer with bidirectional attention, right? So the conformer isn't, this part here is allowed to pay attention to all other parts of the sequence. It's not like this little part here is only limited to this part here. During training, an RVQ level Q is sampled. Okay, so Q is the hierarchical levels of this residual vector quantization, where again, Q1 is going to have the most kind of signal, and as you go higher and higher and higher, there's going to be increasingly less and less kind of signal. And I think that's kind of what they're trying to show here with the coloring. So they're trying to show you that at Q1 you have more kind of information. That's why it's a kind of a deeper, richer color. And as you go higher up, you have kind of like this increasingly faded color. T is going to be the actual frames. So here they were saying 50 frames per second. So you're going to have, I don't know, in 30 seconds of audio, you're going to have 50 times 30 total frames. And then conditioning tokens, this is your actual, like, the text that you want to generate, right? The text that the person is speaking, and then also who is speaking, so the speaker ID, and then the actual text that is being spoken. And I think this is where Oysen said they used the W2V BERT model in order to get these tokens. Okay. And then masked tokens. So these are the tokens that are masked, which means they're hidden, and those are the ones that you actually want to predict, right? So, all right. Subset of randomly sampled tokens. A subset of randomly sampled tokens at level Q are masked together. So it seems like the masking is actually random with all tokens at level Q plus 1 Q. The loss is computed only on the masked tokens at level Q. Okay, so they're taking the audio, right? They're breaking it up into these chunks of time T. So every single one of these kind of vertical things here is a chunk of time T. So you can see here for each chunk of time T, for each frame, they have one conditioning token. They have one token which represents the first level of the residual vector quantization. They have a second token which represents the second level of the residual vector quantization, and so on. And what you see what they're doing here is they're feeding all of these kind of in parallel, right? Then they're doing this bidirectional attention. They have a head for each of the Qs, right? So you see here how those 3 different levels of this Q, of this RVQ hierarchy, and you see how there's 3 different heads. So there's one head for each one. And this is a masked token prediction task. So they're giving you the conditioning in the first level, and then you're trying to predict the next 2. Here they're giving you the conditioning, the first level and the second level, and you're trying to predict the third level. So I think that's what they're showing here with the bolded, is this is what you're actually trying to predict, right? And each head is going to predict the corresponding token for that specific level of the RVQ. Okay, so I feel like I kind of understand all of this, but if you guys have any specific questions. In diffusion models like Stable Diffusion, they typically produce textures when not conditioned. I wonder what happens with audio models. Yeah. What is texture in audio space? Right, that's an interesting question. Masking. For designing our masking and decoding, we extend the masking and confidence-based parallel decoding scheme of mask GIT to token sequences produced by RVQ. Okay, so confidence-based parallel decoding, right? I think we went over this, but it's basically this idea of decoding in parallel and then only picking the ones that have the high confidence and then running the decoding again, and then because now you have more of the sequence filled out, you're going to be able to have higher confidence on some of these other tokens, which means that those will become part of your sequence, and then so on, right? So you keep doing this and the confidence keeps getting higher and higher and higher. 2 token sequences produced by RVQ. At a high level, our approach can be seen as following the strategy of mask GIT per RVQ level in a course-defined order. The course-defined ordering is of particular importance since it not only reflects the conditional dependencies between the levels of the RVQ hierarchy, but also exploits the conditional independence of tokens from finer levels given all tokens from coarser levels. What do they mean by this? The tokens from finer levels are conditionally independent of the tokens from the coarser levels. Is that true? Is this token here conditionally independent from these 2 tokens here? I don't know if that's necessarily true. Not only respects the conditional dependencies between levels of the RVQ, right? I agree with this. I agree that there is some kind of dependency between the different levels of the RVQ because each level of the RVQ is a quantization of the residual of the previous level. But I don't really agree with the second part. They don't consider their model autoregressive, even though it seems to be autoregressive in Q levels. Yeah, that's I was just saying that as well, where I feel like they say it's not autoregressive, but it is. It's just not. It's not autoregressive in this dimension where this doesn't depend on this, right? It's not autoregressive in the sequence level, but it's autoregressive in the quantization level. The tokens of finer levels are responsible for local fine acoustic details and can thus be sampled in parallel without a loss of audio quality. I mean, this makes it sound like it's not autoregressive in the RVQ level either. Right? They're saying, hey, you can be sampling in parallel, not just in the sequence dimension, but also in the RVQ dimension. Schwat. We design our masking scheme for training accordingly. To enable voice prompting, we randomly sample a time step t in the set of 1 to capital T, where there's T maximum steps. We do not mask any token before this time step. The conditioning tokens are never masked. So they never mask out the conditioning token. So I guess that is what this shows you. They're only ever masking out the SoundStorm tokens, these RVQ tokens. Let capital Y, which is in the set of 1 to C, and the dimensionality of that is T by Q, where T is the total amount of time steps, and then Q is the number of RVQ levels. And then C is the codebook size used in each RVQ level. What? There's a different codebook size for each RVQ level. Okay. I know what they're going to be doing. So, yeah, that's really what they meant here. So, at the very beginning of this paper, right, they talk about how taking into account the special structure of the input is going to lead to efficient training and inference, right? So, they know that the RVQ levels, the higher up you go in this hierarchy of RVQ levels, the less important these tokens are, right? So these like light peach colored tokens, not anywhere near as important as these the first level of the RVQ. So what they're going to do is they're going to have a different codebook size, right? So the codebook size for the lower RVQ levels is going to be much higher than the codebook size for the higher RVQ levels, right? That's actually quite clever, right? So yeah, they're going to have a different tokenizer basically for each RVQ level, and the tokenizers are going to become kind of increasingly smaller and smaller code books as you go higher up in the RVQ level. Sample the prompt delimiter time step. Okay, so you have our masking scheme proceeds as follows. Okay, so this is how they're doing masking. First thing they do is they sample from this time step. Here, this script U means uniform distribution, which basically means an equal probability of selecting any of the time steps between 0 and t minus 1. Sample the current RVQ level. Okay, so again, you're randomly picking one of the RVQ levels. This script U just means a uniform distribution. Then you sample the mask. So M is either going to be 0 or 1 according to a cosine schedule. Okay, for level Q. So you have a cosine schedule is just a schedule that goes kind of like up and down and up and down and up and down, right? Cosine wave just looks like this. So whenever you see something that's a cosine schedule, it just refers to the fact that it's going to be going up and down and up and down and up and down with some specific period. Sample the masking ratio P equals cosine U, where U is, okay, so the ratio, the number of tokens, I guess, that you're going to mask at any specific point in time is going to depend on, basically, you sample U from this uniform distribution from 0 to pi over 2. That gives you the cosine. This number is always going to be between 0 and 1, and that's going to be your ratio. So you basically pick your ratio based on this. And the sampling IID for MI, for the mask, is the Bernoulli. So one thing to think about, right, is like, why are you using a cosine schedule as opposed to just like picking a random number between 0 and 1? And the reason people do that is because sines and cosines, right, they bounce between 0 and 1, but they don't do so. They do so in a specific way, right, where you're actually spending a little bit more time in the 0 and the 1, right? It's like if you think about this, right, like if you're sampling randomly from this schedule here, you're not going to sample 0 as often as you're going to sample negative 0.8, right? It's like there's kind of like because it slows down as it kind of gets to the top here, and it slows down when it kind of gets to the bottom here, and it kind of and it's at its maximum speed in the middle, you're going to end up with a distribution that's a little bit more tricky. It's a little bit more kind of like, it tends to be more on this negative 1 to 1, like close to those ends, which is what they want, right? I read that as C is the same for all RVQ levels because Y is a matrix with dimension, has values from 1 to C. Not too sure, though. Okay, so you're saying I might have... C might be the same? Y equals 1 to C denote the SoundStorm tokens, where C indicates the codebook size. So each token... I don't know. I think if the code books are different, they'll probably say it. So for now, let's say that we do not know if the code books are different sizes. Mask the selected non-prompt tokens at the current RVQ level Q. Okay, so non-prompt tokens, I think, is the tokens that are not the conditioning tokens, not the text tokens, basically. At the current RVQ level Q. The mask of YT prime Q if MT prime is 1 and T prime is greater than T, and all non-prompt tokens at finer RVQ levels. Mask the selected non-prompt tokens, okay, at the current RVQ level Q, so at a specific RVQ level, which you picked right here, right? Q, you sampled it from a uniform distribution between 1 to Q. Y, T, Q, if MT equals 1. Okay, so basically, this schedule is going to basically give you a number between 0 and 1, and they're saying only when it's equal to 1 do you mask the token. And then T prime greater than or equal to T. I think this just refers to the time step. Okay, there's a lot of weirdness going on there. Given a masked token sequence, we train the model with cross-entropy loss. This is your standard classification, is usually cross-entropy loss, with the ground truth tokens as target, where the loss is only calculated on the masked tokens within the Q RVQ level. Okay, so why cross entropy? Because at the end of the day, what your model is predicting is it's trying to pick the right token, right? So you have a code book of all possible tokens, and for each possible token, there's going to be a confidence, right? And then much like in a classification model, you have all the possible classes that can be output, and you have basically a confidence score or a kind of a logit for each individual class. Use a cross-entropy loss to say this is the class that should have had a confidence of 1, right? The highest confidence, and everything else should be a confidence of 0, right? And this is a similar kind of thing, except rather than predicting 1 out of 1,000 ImageNet classes, what you're trying to predict here is which of the tokens out of the however many tokens there are in my code book is the one that I should have predicted. The loss is only calculated on the masked tokens, so they only push gradients, or no. They only calculate the loss on the masked token. So It means that they're masking specific parts of this cross-entropy loss. I'm not entirely sure. Within the qth RVQ level, an example of this masking scheme is illustrated with t equals 4, q equals 3, t equals 0, and q equals 2. So in figure 1, capital T equals 4, which is we randomly sample a time step where t denotes the maximum sequence. So there's 4 total time steps. Okay, I understand that. Q equals 3. So there's 3 levels of quantization, that makes sense too. Capital Q equals 3, there's 3 levels. T equals 0, so lowercase t is the time step that you're sampling, which is this very first one here. Okay, I guess that makes sense. And Q equals 2. Okay, so the Q equals 2 refers to the fact that you only mask the tokens after that. I think that's what they were doing here. Yeah, that's what they were trying to describe here. So you get a specific level Q, and then you only mask out things at finer levels. So if your Q is 2, you're only going to mask out things at a finer level than that. You're not going to mask out the tokens at Q equals 1. Yeah, which is the whole kind of, it's autoregressive based on the Q or RVQ dimension. Okay. Iterative parallel decoding. Given a conditioning signal, our decoding scheme starts with all SoundStream tokens masked out except for the ones in the prompt. Then it proceeds to sample the tokens RVQ level-wise in a coarse-to-fine order. Right, so it starts with the lowest level and then goes to the next level and then goes to the next level and then goes to the next level. Only proceeding to level Q plus 1 when all tokens for level 1 to Q have been sampled. I wonder if you could do this in image space. I guess RBG isn't really the same thing as RVQ level 1, 2, 3. We use the confidence-based sampling scheme of Chang et al., which is the masked GIT. We perform multiple forward passes, and at each iteration I, we sample candidates from the masked positions, retaining PI of them based on confidence scores. Okay, so it's not actually a threshold. It's not like there's a threshold for the confidence. What they're doing is they're just sorting them based on the confidence and then picking the top PI of them. Okay, that's kind of interesting because I thought it would have been a confidence score, like, okay, anything above a 0.7 confidence, we're gonna accept it. But it's not. That very first step, the confidence are probably going to be all very low, right? So that's kind of interesting. Where PI follows a cosine schedule. So going back to this, right? Like initially you start, I feel like the confidences are all going to be low, but at some point, right, there's going to be some knowledge here that says, okay, the I, right, the token that represents the I of this flamingo, I'm just going to say the token that represents the I is generally going to be in the middle, so the confidence for the I token being in the middle is going to be slightly higher than pretty much all the other tokens, so therefore that's the one that's going to get kind of like sampled first, and as soon as you have the I token and you know, okay, the I of this flamingo is right here, then everything else starts to fill in quite quickly. But that first kind of step is going to be, I feel like, very low confidence. So you, like, I would almost say you want it to kind of almost be a little bit more random than that, right? I don't know. Compared to the masked GIT, we use a greedy decoding instead of a confidence-based sampling for the last iteration between each RVQ level, which we found to improve the perceived audio quality. So I think greedy decoding is when you just do all of it. They described it higher up here. I already lost it. At some point they described exactly what the greedy decoding is. Greedy decoding generally means you just pick the highest one every time, the one with the highest confidence. Performing the decoding RVQ level-wise makes it possible to exploit the conditional independence assumption in finer levels. namely that multiple finer tokens can be sampled in parallel since they represent local fine acoustic details. Okay. This makes sense. Okay, so before I was confused because I was like, the finer tokens are not conditionally independent from the lower resolution tokens, the coarse tokens. So what is going on? But that's not what they were talking about. They're saying the conditional independence of the finer tokens to other finer tokens. That makes sense, right? So what they're saying is that this token here, this fine token right here, is conditionally independent of this fine token here, right? So they're saying that this token at RVQ level 3 is conditionally dependent on this same little frame RVQ level 2, which is conditionally dependent on RVQ level 1 on this same frame. But RVQ level 3 at this frame here is conditionally independent from RVQ level 3 at this frame here, which is actually not entirely true as well. There is probably a very small a small amount of information and kind of conditional or dependence, right? Like this token here is going to in some way depend on that token there, but it's so small that I think this assumption that they're independent is probably fine. This implies that we can decrease the number of forward passes significantly as we progress to finer RVQ levels during decoding. Okay, so if you're doing them in parallel, you don't need to worry, and you can do them all in parallel because the finer you get into this RVQ hierarchy, the more that they're independent and the more that you can do it in parallel. So that's a nice little trick. Experiments. Model training and inference setup. In our experiments, we rely on a SoundStorm codec that produces 50 frames per second and uses an RVQ with a Q of 12. Yeah. 1024 codebook size, so that's a pretty small codebook. And it's per level, so Oizen, I think you were right. I think they use the same size codebook for every level, resulting in a bit rate of 50 times 12 times log base 2 of 1024, which is around 6,000 bits per second. Right? So what the fuck is this log base 2? It's because every bit inside your codebook you can represent with 2 bits. So therefore, the total amount of bits of this is that. So they're basically just converting into bits, right? And computers operate on this binary system, this base 2 system. So I don't really know if this is good or bad. Like I don't know what is a BPS for like just normal audio. What would be the BPS for a audio streaming service like SoundCloud or Spotify? Okay, here are some common bit rates for audio streaming services. So 32K BPS is probably kind of watching a YouTube video on shitty quality, and then 320K BPS is Hans Zimmer sitting in his studio listening to like a $10,000 piece of audio equipment. Okay, so what is this? This is 6,000 BPS, and if you convert it into K BPS, it's 6K BPS. So 6K BPS, still very shitty. It's still not super good, right? Still basically 1/4 of the lowest bit rate which you can get from SoundCloud or Spotify, but it means that we're close, right? That's the same kind of order of magnitude. So we're getting there, right? We are getting there, and the ability to generate audio is now kind of at least within the same order of magnitude as kind of what you would be able to get from kind of a streaming service. We use the semantic tokens of audio LM as conditioning, which originate from WTV BERT. Damn, dude. Oizen, I think you read this paper beforehand. I think you're secretly cheating, and you already read this paper, and that's how you know what tokenizer they were using, and the fact that the code books were the same size, and the fact that there's 12 levels of quantization. I don't think that's allowed. I think we have to. You got to read it first time. with k-means with 1024 cluster centers. Okay, so what do they mean by this? Is that whenever you're tokenizing something, you're converting it, you're projecting it from the original representation into a compressed representation, right? You're mapping it into a lower dimensional space. And in that lower dimensional space, you're going to define specific points, right? You're going to say, here's one point, here's another point, and there's 1024 of those. So then whenever you take a new piece of audio and project it into that compressed space, right? You're going to say, which of these is it, right? Which of these centers is the closest one to it, right? And then from that, you're going to say, okay, well, this new point, this new embedding that I found, I'm going to refer to it with respect to these already pre-existing 1024 centers. These tokens have a rate of 25 tokens per second, so we duplicate them to match the frame rate of SoundStream. I guess this is the speed at which you can use the WT BERT tokenizer, or W2V BERT. We use a conformer with 350 million parameters, 12 layers, 16 attention heads, and the embedding and model dimensions of 1024, of course, because that's the size of their codebook. Feed-forward dimension of 4096, convolutional kernel size of 5, and rotary positional embeddings. So again, positional embeddings are the additional embeddings that let the transformer know at which specific point within the sequence this particular embedding comes from. During decoding, we use 16 111 iterations for the RVQ levels, so 16 iterations for the first level, and then greedily choosing tokens with the highest probability in the subsequent levels. Okay, so obviously, right, this whole paper, they're trying to like kind of present to you this idea that the whole point of this RVQ is that the first level of the RVQ is where all the juice is at. That's where all the information is at. So they kind of double down on that, and they say we're going to spend way more time on this first level, and then all the subsequent levels after that, who cares? We're just going to spend one iteration at that. This strategy results in 27 total forward passes, with the model to predict 30 seconds of audio. I like how many numbers they have here. Like, that's kind of cool. You know, I like when people just put numbers directly here. You don't have to go all the way to the appendices to get all these numbers. Or the equivalent of 18,000 SoundStream tokens. So it's predicting 18,000 tokens in 27 forward passes. They train the model on Libri Lite. What is this? Libri Lite. Libri Lite is a Facebook dataset, which is a benchmark for the training of automatic speech recognition systems. It contains 60,000 hours of unlabeled speech from audiobooks. Okay, so it's basically just a bunch of people reading audiobooks. MIT license. You know, this is actually really promising, because if they trained this entire thing on just one data set that's like a public data set of only 60,000 hours, there's probably way more audio data than that. You know, think about what if they trained a model that was 3 times bigger on probably 10 times more data. I feel like you could get 10 times more data than this. So that's kind of, I like that. To me, the fact that they trained this on a relatively small data set, that's good. That means there's a lot of room to grow. There's a lot of room to scale. 10 epochs over the data. Epochs are basically just how many times you look at the data, right? So a model that's trained on 1 epoch has basically seen every single data point once. A model that's trained 2 epochs has seen every single data point twice, and so on. Sampling random windows of length between 0 and 30 seconds from each sample. Okay, so epochs and random windows of length are different, and this is why it matters. So when you're doing, for example, in computer vision, you're doing any kind of training with images, right? You'll have many epochs, right? 100 epochs even, right? And why can you do that many epochs? And the reason you can do that many epochs is because usually you have data augmentation, right? You're corrupting the images, you're changing the appearance, you're cropping them, you're sliding them, you're stretching them. So even though the model has seen each image hundreds of times, it's not actually the same image. It's like a random version of that image that's like kind of weird and augmented and morphed, right? So this is the same thing. It's like even though they trained on this data set for 10 epochs, every single epoch they probably got a new random window of each data point. So and they didn't even say that they're doing any kind of audio augmentation, which is another thing you can do. I think in audio you can add like noise, you can probably fuck with the different coefficients, like add different types of weird background sounds. So there's a lot of room to grow here based on what they describe here. Like they use a relatively small data set and they don't do any augmentation. So I feel like you could do this same paper, but use a much larger data set, a bunch of different data sets, and then have a bunch of augmentation on top of that. And I feel like you could scale this significantly. But that's not what this paper is about, right? They don't necessarily care. That what they're really kind of trying to showcase is the speed, right? This is like a model architecture paper. They're trying to say, look how cool our model architecture is, look how much faster it is, and so on. They don't necessarily care about producing the best possible audio generation model that you can. In a series of subjective evaluation experiments, here he is referencing his own work again, have shown that the acoustic generation stage of audio LM produces audio with quality indistinguishable from the quality of the audio samples. I wonder if there's a formal definition for indistinguishable in the audio world, right? Because I'm sure like a normie like me might not be able to distinguish the quality, but I'm sure like someone like a Hans Zimmer, like a professional like audio producer type person would probably be able to distinguish the quality. We consider audio LM's hierarchical acoustic generation stages as a baseline in our experiment. One important difference compared to audio LM acoustic stage is that we require the conditioning signal to be time aligned with the sound stream frames. Yeah, the tokens need to correspond exactly with the RVQ tokens. Whereas the experiments use semantic tokens with duplicate removes. For a fair comparison so that both methods use the same conditioning, we repeat the acoustic stage experiments without removing duplicate semantic tokens, thus making the conditioning stronger. We also use the same SoundStream codec for both methods. So this is the actual audio codec that they're using, the neural audio codec. Speech intelligibility. We quantify speech intelligibility by measuring the word error rate and character error rate for the generated audio. Okay, so I don't really know what these metrics are, but let's ask our good old friend Bart here. Explain WER and what was the other one? WER and CER. Like IM5. So part of why I did it like this too is that I want to see if it, word error rate, character error rate. I wanted to see if it actually understood what those acronyms were. Because if it didn't and it made up new acronyms, then I knew it would be hallucinating, right? So sometimes you got to ask the question in a way that gives you a way to confirm that it actually knows what you're talking about. Okay, WER is counting the number of words that are incorrectly recognized, divided by the number in the total, so it's kind of like a precision kind of thing. And then CER is character error rate, number of characters that are incorrectly recognized. Okay, so characters, I guess, is the people, like the characters, or characters as in individual letters in a word? I think it's individual letters in a word. I don't know if characters here refers to like people. The generation is conditioned on the... Let me drink some coffee. Drink some water. All right, let's keep going. The generation is conditioned on the ground truth semantic tokens from Libri Speech Test Clean Split. Okay, so that's probably the reason they use this data set, is that it already came pre-tokenized. GANs are probably the fair judge. Yeah. We perform these experiments both in the unprompted setup, where the method can randomly sample speakers, and in the prompted setup, where the methods should respect the speaker identity provided in the form of ground truth SoundStream tokens corresponding to the first 3 seconds. We use a conformer transducer L for transcription. I think ASR stands for automatic speech recognition. We report the results separately on short, medium, and long, so 3 different durations segments. Since Audio LM's acoustic generation stage is autoregressive in the flattened token sequence of the first 4 RVQ levels, it is prohibitively expensive to generate 30 seconds in a single pass. Yeah, so here you finally have them admitting that even though they spent this entire fucking paper talking about how they're not autoregressive, here they are finally admitting that they are autoregressive, but they're autoregressive in the RVQ level space. So somebody needs to do a non-autoregressive in the sequence space and non-autoregressive in the RVQ space. Hence, we generate segments longer than 10 seconds with a slide and prompt approach. Okay, so some kind of sliding window where we generate 10-second chunks and then use the last 3 seconds as the prompt for the next chunk. Okay, kind of standard there. The results in Table 1 show that SoundStorm improves over Audio LM's acoustic generation significantly in terms of WER and CER on both splits. So both of these metrics are error rates, so generally lower is better, right? So WER lower is better, CER lower is better. Audio quality, I don't know what the metric for this is, but higher is better. Voice preservation, acoustic consistency. Okay, so they're comparing against their previous work only, so it's kind of a little bit harder, but it's better than their previous work, which, I mean, is kind of a no-brainer. Of course, it's going to be better than your previous work. But it's honestly not that much better. But I think that's what they want, right? Even here, for the short sequence, audio quality is better with their previous work. The whole point of this paper wasn't, hey, we're trying to push the state of the art in terms of the quality of the audio. The whole point of this paper is like, hey, we're trying to make this original paper that we had significantly faster by removing this autoregressive within the sequence space. So really what they want to show you is that the quality is basically either the same or slightly better. We report metric values, splits, and SoundStorm matches Audio LM's generator and outperforms it in terms of speech intelligibility and acoustic consistency. I don't know about this outperform. We're talking like 0.03. You know, this one's exactly the same. So it feels like it's kind of about the same performance, but maybe this one here's a little bit better. I don't know what voice preservation is, though. Like, that might just be kind of like a bogus metric, to be honest. Next, we measure the capability of SoundStorm to maintain the speaker identity of the prompt. Okay. To do so, we extract the speaker embeddings from the prompt. So speaker embeddings is some kind of vector, some kind of embedding that represents who the speaker is in this particular segment of audio, right? So they're going to do that with cosine similarity. So they're going to get the speaker embedding from, I don't know, the first 3 seconds, and then the speaker embedding from the next 3 seconds, and they're going to say, okay, these two embeddings, aka these two vectors, should be very aligned, which means that the cosine similarity is going to largely tell you kind of the angle between those, right? And the angle should be small, right? They should be very similar. That's all cosine similarity is. It's basically literally the Pythagorean theorem of vectors. Maybe not Pythagorean theorem, but like it's basically what you learned in like elementary geometry, right? Where you have basically like the cosine is the angle between the two things, like that, right? We compute embeddings with a publicly available speaker verification system based on wave LM. Okay, so this is how they're actually getting the speaker embeddings. In the case of long generation, it is interesting to measure to what extent the acoustic properties of the prompt are preserved a long time in the generated audio. Okay, so acoustic consistency drift, they basically want to see that over in these longer sequences of like 30 seconds, does the speaker identity change over time? And honestly, I feel like that happens normally, right? There's probably there's probably an acoustic drift, whether or not in like natural audio, right? It's like if someone's doing a 2-hour stream like I'm just doing here, the speaker embedding at the beginning of the stream is going to be different from the speaker embedding at the end of the stream, because I'm going to be getting more tired, I'm going to be getting more warmed up. It's like the tone and the nature of my voice is going to naturally change as I go further and further and further and further into an audio clip. So I don't think that you necessarily want it to be the same exact speaker embedding the entire time, right? That's almost like unnatural. And that's actually interesting too. It's like there's probably a whole kind of rabbit hole of like, how do you model the change in the speaker embedding over time, right? How do you condition the speaker embedding with the time of day, with the amount of time that this person has been talking, and so on, like all these different variables that'll allow it to change, right? Which is kind of cool. I don't think anybody's ever really thought of, or I've never seen any work where people do that. We consider a speech corpus in which the example contains recordings from a single speaker and extract two random non-overlapping crops. Okay, so this is where they're going to get the embeddings. Then for each crop, they get the embedding pre-trained on the same corpus, specifically layer 4 of this best RQ model. Each sequence of embeddings followed by global average pooling along the temporal dimension and a linear projection layer so that each crop is represented with a single 1024 dimensional embedding. So pooling is a technique where if you have a lot of things that are coming in from a lower level of a neural network, you can basically pool them and say, okay, well, I only want specific ones of that. So like pooling convolutional neural network, I feel like this is the best. All of my mental models are based on convolutional neural nets. This is average pooling. So in average pooling, you have an 8x8 feature map here, and you basically take the average of each of these 4 and you get this, and this is pooled, right? Max pooling is whenever you take the maximum for each of these and you get that. And what is the point of pooling? The point of pooling is that you reduce, it's a way to reduce the size of something, right? So before here you have an 8x8 square, you know, that's annoying. You got a lot of information here. So now max pooling allows you to compress that into 4, so it's a lot easier to deal with. And generally you see pooling at the very last layer, right? So generally the pooling happens at the very end. So you have a bunch of convolutional layers, right? And as you go more and more convolutional layers, the depth of the kernel just increases. You're getting these feature maps that are kind of bigger and bigger and bigger, more numbers, and at some point you're going to want to flatten it and to put it into a multi-layer perceptron. And if you flatten this last feature map here, you're going to blow up your memory, right? Because every single point has to be connected to every single point in this MLP. So you're going to pool that so that it's smaller, and then you flatten it. So kind of sorry for that tangent, I guess, there, but that's basically what they're doing here. They're taking the layer 4 of whatever this model here is, then they're pooling those in the temporal dimension, and then projecting them into 1024 dimensions. To measure acoustic consistency drift, we compute the cosine similarity between the embeddings computed from the prompt of 3 seconds and the embeddings computed from the subsequent crops of 3 seconds along the temporal axis. Okay, so they're basically comparing with cosine similarity the embeddings of the speaker embeddings as you go along this sequence. We observe that for the audio generated by SoundStorm, the acoustic consistency score is closer to the one measured for original samples, while for audio LM, we observe a more significant drift over time. Acoustic consistency between the prompt and the generated audio for the samples in the long split of the Libre speech test clean. The shaded area represents the interquartile range. So this is the acoustic consistency, aka cosine similarity between the speaker embeddings. You have here the original audio, and this is kind of what I was saying. If you actually look at that, the original audio itself isn't a perfect flat line. It's actually changing over time, right? The speaker embedding at the very end is different from the speaker embedding at the very beginning. But here, largely what they're showing you is that SoundStorm and Audio LM are different here, where SoundStorm is much closer to the original drift compared to Audio LM, which quickly kind of drifts away. The acoustic consistency score is close to the one measured for the original samples. Audio quality. We use MOS estimators similar to DNS MOS. What the fuck is MOS? To estimate the perceived audio quality of the generated samples. What is MOS for audio quality determination? According to MOS estimator, SoundStorm is on par with acoustic generator with the original Audio LM paper, which in turn has been shown to match the quality of the ground truth audio. MOS stands for mean opinion score and is a subjective measure of the perceived quality of audio. Okay, so basically you have a bunch of people sit there and listen to audio and then tell you, typically obtained by having a group of people listening to the audio samples and rate them on a scale to 1 to 5. So it's like Amazon store ratings, 1 to 5 stars. Okay. So according to Amazon star rating, the audio quality for short sequences, mid sequences, and long sequences, the short sequences are actually much lower perceived audio quality compared to the longer sequences. Okay. Subjective studies. Runtimes of SoundStream decoding. So the sequence length, so the total amount of audio in the sequence, so 10 seconds, 20 seconds, 30 seconds, which I think is corresponding to the short, mid, and long. And then you have the total runtime in terms of the actual time it takes to generate the audio. You have SoundStream decoder, which is the neural audio codec that they're using. You have Audio LM, which is the original version of this paper, and then you have SoundStorm, which is this paper. So largely what they're trying to show you here is that SoundStorm is much faster than Audio LM, which is the previous ones. And I guess they're also showing you, for comparison, the speed of the SoundStream decoder as well. Runtime and ablations. We measure the runtime of different methods to generate 30 seconds of audio on a single TPU v4. Figure 3 shows that SoundStorm can generate audio 2 orders of magnitude faster than Audio LM's acoustic generator, with a real-time factor of 0.017, including decoding to waveform by the SoundStream decoder. Okay, so SoundStorm includes the decoding step as well. We also measure the runtime of the semantic generation stage and conclude that by coupling the semantic generation stage with SoundStream, we can generate 30 seconds of speech within 2 seconds. Okay, so here's where they actually break down why there was a difference in the 2 seconds versus 0.5 seconds in the abstract, right? In the abstract, they said 0.5 seconds and 30 seconds and then later they said 2 seconds. So it was like, why is there a difference there? And the difference is because in the 2 seconds it takes to generate 30 seconds of audio, you're spending 1.4 seconds just taking the text and tokenizing it into the actual semantic tokens. So actually the bulk of the time is spent creating these semantic tokens, these context tokens, I think they were calling them. The SoundStorm, which goes from the semantic tokens into the audio tokens, right, the neural audio tokens, that only takes 0.5 seconds. And then going from the audio tokens, right, the neural audio codec tokens, the SoundStream tokens, into actual raw audio waveform takes 0.1 second. So it actually seems like there's a lot of opportunity to make this semantic token generation faster, because that actually seems like the weakest link in the chain. Number of decoding steps. In the former experiments, we used 16 iterations for decoding the first RVQ levels and performed greedy decoding for the subsequent levels. This is what we saw, that they're spending the majority of their kind of effort on the first RVQ level because that's kind of which has all the information, or the most information. To achieve this, we repeat the speaker-prompted experiment with different numbers of decoding iterations in the first level. Shows that according to the audio quality estimator, our strategy of using 16 iterations achieves an increasing 0.0.12 compared to the level-wise greedy decoding, whereas further increasing the number of iterations does not improve the score. The artifacts produced by the greedy strategy are clearly perceivable. We have also experimented with increasing the number of iterations for RVQ levels 2 through 12. Okay, so they're like, what if we spent more effort, more iterations on further quantization levels? Would we get an improvement in audio quality? And they say, nope, you do not get an improvement in audio quality. We hypothesize that performing multiple iterations on finer levels becomes relevant when generating audio beyond speech, where the semantic tokens will not capture all the important acoustic details. Okay, so maybe if you're doing something that's not just speech, maybe you're trying to generate like a full orchestra or something like that, then at that point, spending multiple iterations for finer RVQ levels would be worth it. Right, and audio is kind of infinitely high resolution. You could basically just keep going more and more and more and more, and that's probably what will keep happening. Although at some point the human ear just can't perceive the difference in quality, and then at that point you're pretty much set. And I think that's why like a lot of people meme on like audio codecs that are like very intense, like the FLAC. Where is it? FLAC. Because the reality is that like most humans can't tell the difference between super high quality audio and like medium quality audio, right? It's similar to like when you go to get like an eye test, right? And you go and you look, right? At some point, like you could keep making the screen on your phone like higher and higher resolution, but like most people are not going to be able to tell the difference. And the same thing happens with audio, where like the ability to perceive audio quality is kind of like a bell curve if you had every single human's ability to perceive audio quality. So really you just want to target the center of that bell curve, because most people are not going to be able to tell the difference if you go beyond that. Spoken audio synthesis is an important application where maintaining speaker identities over multiple speaker turns and long time spans is of paramount importance. This makes it an ideal use case for SoundStorm. In this section, we show that by coupling SoundStorm with a text-to-semantic token model, we can synthesize high-quality multi-turn dialogues for up to 30 seconds. So, because you're conditioning each frame of audio generation with a token or with an embedding that includes the speaker embedding, you can basically switch from one speaker to another very easily, and you can do this kind of back and forth, which is what they were showing you here. Right, where this 30-second audio generated, this 30-second of audio that they generated is actually two different people speaking to each other. We collected a corpus of approximately 100,000 hours of dialogue segmented into 30-second chunks. By running an off-the-shelf speech recognition system, we generated a transcript for each segment. In these transcripts, speaker turns are annotated with a turn marker symbol in the appropriate location in the transcript. Okay, so there's some kind of token that represents specifically when a person stops talking and when a new person starts talking. So very similar to an end of sequence token or a start of sequence token in whenever you're tokenizing text for LLMs. We train a 0.6 billion parameter best RQ on this data set and fit k-means with 4,096 cluster centers. So this is the speaker ID, I think. This results in 25 semantic tokens per second with a codebook size of 4096. We train a SoundStorm codec operating at 24 kilohertz, producing 50 frames per second. So the actual neural audio codec that produces the raw audio wave is producing audio with a sample rate of 24 kilohertz. But the tokens that are used in or fed into the SoundStorm codec model are only at 50 frames per second. So that's the big difference there. It feels like a lot of the actual raw audio generation is being done by this SoundStorm codec, right? Not only is it super fast, right? Because the actual decoder here is only 0.1 seconds for this SoundStorm neural audio codec, but it's going from 50 frames per second to 24,000 frames per second, basically. So this SoundStorm codec is pretty badass. To model the text to semantic token mapping, we train a BiT5 large transformer. Okay, so this is the actual transformer architecture that they're using. This is a encoder-decoder model with 36 encoding, 12 decoder layers, embedding size of 1536, and a feed-forward dimension of 3840. In total, the model has 1.2 billion parameters. We only train the decoder and use a text pre-train encoder from a published BiT5 checkpoint. So this is the actual W2V encoder that they talk about here, the W2V BERT, which is what they're using to convert the text into these semantic tokens. So that model has over 1 billion parameters. This model takes a byte level representation of the text and predicts non-duplicated semantic tokens. Non-deduplicated, so they don't get rid of duplicate ones. Decoding is done by temperature sampling with a temperature of 0.9 and top K set to 125. So anytime you're decoding, right, you're basically taking something, you're trying to predict the actual token. Which of these tokens out of all the tokens in my codebook am I going to basically predict? And this temperature sampling is also done in LLMs, in autoregressive LLMs, right? So whenever you're setting that little temperature in your GPT API, this is the same thing, right? Top K means that out of all the possible tokens in your codebook that could be predicted, you're picking the top 125 of those. Due to the modest size of the decoder and the shortest target sequence length, only 750 semantic tokens, running inference on this model takes 1.4 seconds on a TPU v4. Yeah, so this is what we were noticing here, is that actually the bulk of the 2 second that it takes to generate audio is actually taking the text and turning it into these semantic tokens with this 1.2 billion parameter BiT5 transformer. So it's kind of interesting to me how, like, this paper here, what is it called? SoundStorm is really only like the middle chunk of a pipeline, right? the first part of this pipeline, going from text into semantic tokens, is being done by this byte 5 large transformer, which is pre-trained, and then going from the third part of this pipeline is the SoundStorm, which is actually going from the neural audio codec tokens into actual raw audio waveform. So it's like the beginning and the end of this entire pipeline is pre-trained models that are not part of this paper. And this paper is really only converting in between those semantic tokens and the audio codec tokens. So it's really just like one little piece of this puzzle. They're using different semantic tokens. Okay, so not only... Yeah, they're going to have a different model. If you change the semantic tokens or whatever you're using to create these semantic tokens, you're going to have to use a different model. We trained both the text-to-semantic model and the SoundStorm on the dialogue corpus for 10 epochs. Okay, that's kind of interesting. So they don't... I'm wrong. I was wrong in saying that the text-to-semantic model and the SoundStorm were pre-trained models that they just used out of the box. That is not the case. They took SoundStorm and text-to-semantic and trained them from scratch on the specific dialogue corpus that they had. So it's not like they just used out-of-the-box versions of those two. They actually trained their own versions of those two specific for this. I don't know if that's good or bad. I feel like they might have even left some performance on the table by doing that. We recorded short exchanges serving as prompts. We created text transcripts. We then feed the text transcripts to the text-to-semantic, the output of which is fed to SoundStorm while using the speaker prompts for both stages. We find that this approach generates high-quality natural dialogue sequences, generating disfluencies at the occurrence of filler words in the transcript, and allowing for controlled speaker turns through the insertion of the turn marker symbol. So you can pretty much, whenever you want the speakers to switch, you can put this specific turn marker token. The total runtime for synthesizing a segment of 30 seconds is 2 seconds. Conclusion. In this paper, we present SoundStorm, a model that can synthesize high-quality audio from discrete conditioning tokens efficiently. When compared to the acoustic generator of audio LM, SoundStorm is 2 orders of magnitude faster and achieves higher temporal consistency when generating long audio samples. By combining a text-to-semantic token model similar to Spear TTS with SoundStorm, we can scale text-to-speech synthesis to longer contexts and generate natural dialogues with multiple speaker turns, controlling both the voices of the speaker and the generated content. Broader impact. The ability to mimic a voice can have numerous malicious applications. Don't be evil, I guess, is the TLDR there. And do they have an appendix? No appendix. Okay. Pretty cool. So let's look at some of these actual generations here. So dialogue synthesis.
Where did you go last summer?
I went to Greece. It was amazing.
There's like a little bit of a ring to that.
Where did you go last summer?
I went to Greece. It was amazing.
Oh, that's great. I've always wanted to go to Greece. What was your favorite part?
It's hard to choose just one favorite part, but yeah, I really...
The filler words are impressive. Loved
the food. The seafood was especially delicious.
Yeah?
And the beaches were...
The way they like interject with like, yeah, that's kind of good. Quality's pretty good too. It's definitely beyond the threshold where I can really tell the audio quality.
We shall be blown up, but no. The dazzling disk of mysterious light nimbly leaps aside. It approaches Hans, who fixes...
We shall be blown up, but no. The dazzling...
We shall be blown up, but no. The We shall be blown up, but no. The dazzling disk of...
Interesting. So here is unprompted, but I don't think it's unprompted in the sense of there's no tokens. It's basically just unprompted in the sense that the speaker token isn't the same. What exactly do they mean by unprompted here? To generate audio conditioned on the semantic tokens. Okay, so it is conditioned on the semantic tokens, which is the text, with and without 3-second voice prompts. Okay, so this is without a specific speaker, and this is with a specific speaker.
We shall be blown up, but no. The dazzling disk of mysterious light nimbly leaps aside. Fixes his blue eye upon its set. It approaches Hans, who
So these two should be the same. The original and the prompted should be the same.
Mysterious light nimbly leaps aside.
fixes his blue eye.
It approaches Hans, who fixes his blue eye.
And it's interesting because this model is frame by frame, right? Because this model is decoding the audio frame by frame, and it has the same exact semantic token at every single frame for all of these. The spacing of the words is basically exactly the same. That's something I'm noticing here. It's like, even though this is a different speaker than this, the like cadence of the speech is exactly the same for both this speaker and this speaker.
Upon it steadily, it threatens the head of my.
Upon it steadily, it threatens the.
Upon it steadily, it threatens the.
You see that? Yeah, the quality is very impressive. It's like, it's basically, I can't tell. To me, this is like perfect audio quality, right? It's like, to me, it sounds good. It's about as good as me listening to a podcast on YouTube. It's the bar for quality, 100%. I feel like they've reached it, and I don't feel like you necessarily need to get higher quality. Maybe if you're like doing like sound mixing for like a movie or something like that, or you're someone who actually has you're someone who is gifted with very talented ears and you can tell, then maybe it's worth trying to get higher audio quality, but to me it's the same. I also like the
law of that school is that everything shall be seen clearly.
The law of that school is that everything shall be seen clearly.
Yeah, I think maybe one negative that I see from this is that, going back to what I was saying with the frame by frame, right? Because this is frame by frame, the cadence is exactly the same. And I think that actually when you look at different speakers, part of what makes people speak differently is the cadence at which they speak, right? Like there's certain people that the way they pronounce certain words and the way that they speak, it's like some sounds are closer together and some sounds are further apart. But in the way that this is done, because it's done frame by frame, you're not going to be able to do anything with that dimension. Everybody's going to be speaking at the same exact cadence. So that's maybe something that they missed out on a little bit, but I don't know. To me, these seem pretty good. So what is this? When generating an audio, higher acoustic. Okay, so this is the original paper. So this is the actual audio. This is their original paper, and then this is the SoundStorm.
There was infinite skepticism around him on the subject. There was infinite skepticism around him on the subject. There was infinite skepticism around him on the subject. There was infinite skepticism around him on the subject.
I mean, I don't know. Those sound the same to me. It's hard to pick out individual things. Automatic dubbing incoming. Yeah, you can already do automatic dubbing. I had like a little project that I made where I basically was using 11 Labs. You guys know this website? It's like an API, and you can basically just text to speech, and you could have your own speech, your own. What did I use for this? Did I use Google? Yeah. So I have my own voice. Let's see this. Testing. Welcome to another Hoopo stream. Let's see. Something went wrong. Oh my God, come on. You are not permitted to use instantly cloned voices? Dude, this is literally my own voice. What are you talking about? All right, I guess they changed their terms, and now you probably need to get special permission to use people's voices. This is part of the problem. I kind of stopped doing this project, and obviously one of the reasons is because I love switching projects, you know, kind of the standard kind of problem that you constantly, as soon as you start a project, you want to do a different project. But another reason I was kind of hesitant to keep going down that project is that the sound stuff is like probably going to get regulated pretty hardcore. You know, like, people don't like the fact that you can generate audio from a famous person, and I suspect that this might be some of the first stuff to be like regulated, and you might even see people like go to jail for like shit like that, you know, like making fake Biden things or making fake Trump things. So I don't know, audio's a little bit sketchy, you know, like, especially with the fact that you have what was that one model that like somebody made like a fake Drake song, you know, like the person who made the fake Drake songs can get sued to infinity. So there's too many people with too much money in the audio world that I feel like if you fuck around, you're going to find out and they're going to sue you. So maybe a word of caution there. But hey, if you like audio, don't let my fear-mongering prevent you from pursuing your dreams. Cool. So that was SoundStorm, Efficient Parallel Audio Generation. Paper out of Google. Very cool kind of little paper. Really what they did is they got rid of this autoregressive style, which you see in a lot of sequence-to-sequence models, where basically every single token that you predict is conditioned on the previous tokens. And the way that they did that is by getting rid of the autoregressiveness, which means that they can do it in parallel. They also used this RVQ, this residual vector quantization, which is a way of quantizing raw audio by quantizing the residual and then quantizing the residual of the residual and so on. And that allows you to basically focus more on this first quantization than the second quantization, than the third quantization. So that gives you a little performance boost as well. And then they break it up into frames so they can do it in parallel, but also so they can condition on a speaker at each individual frame, which allows them to switch speakers quite easily. Cool little paper. There is no GitHub for this. Unfortunately, I don't think there's going to be a GitHub for this because I doubt they'll get permission to publish this. But hey, it doesn't sound like they trained it for very, very long on a very huge data set, so maybe you can actually re-implement this yourself and train it on bigger data sets and then go from there. Make an open source model and release it to the community. Cool. Thanks for listening. Like and subscribe as always. And join us tomorrow. Tomorrow we're going to be looking at a diffusion is flawed paper, which should be kind of cool. This is the paper we're looking at tomorrow. Stability and Hugging Face are sponsoring an implementation. What do you mean by sponsoring? Like they already have someone getting paid to do it, or SoundStorm Stability AI? I don't know what you mean by that. Lucid Rains. Here you go, boom. There you go. You didn't even have to wait. Look at that. Somebody was real fast with this. Boom. I feel like I've seen this name before. Lucid Rains. Yeah, dude, this guy's badass, dude. Holy shit, dude. Yeah, this is probably way good. Definitely use this one. Don't re-implement it, because this guy's for sure this guy's implementation of it is better than whatever you're gonna be able to do. So here you go, guys. It's already done. Oh, here you go. Close the full circle. This guy was sponsored. Okay, so this is the guy who was sponsored by Stability and Hugging Face. And there you go. You can pip install it. Pretty badass. You can help him turn it into a command line tool if you want. It's fucking awesome, dude. I love this. Give them a star. Give this boy a star. I don't know if it's a boy. I apologize if it's not a boy. It sounds like a boy, but not sure. Oh, he's got the attention mechanism on his coffee cup. If you would like me to consider implementing a specific paper, fill out this form. I am Taiwanese American, born and raised in Boston. Full stack software engineer for more than a decade. Worked at Uber. Let's actually see this with this guy. Is this creep on him in LinkedIn? LinkedIn. Boom. Search. Oh, fuck. There's a bunch of Phil Wangs. Which one do you think it is? He said he worked at Uber, right? So let's say Phil Wang Uber. Is it this guy? Yeah, Cornell University. It's this guy. Cornell University, worked at Uber. Let's see. MS Biomedical Engineering. Actually went to med school. That's kind of interesting. Then worked in a pharmacy company. Realized that pharmacy companies are evil. Moved into a software company. Then worked at Uber doing kind of just generic software shit. And then he was a software engineer at some other generic software company here up until 2018. And then since 2018, he's just been, I guess, making money doing his open source stuff. Pretty cool. Nice dude. Cool. That's all I got, guys. Thanks. Like and subscribe. See you later.